Welcome back to the deep dive.
Good to be here.
So today we're opening up a toolbox, and this is one that honestly runs a huge chunk of the modern world, even if we don't always see it happening.
Oh,
We're
absolutely.
talking about machine learning.
Right. And, when people hear that, they immediately brace themselves for either like a super dry math lecture or some wild sci-fi
Here's
speculation.
robots taking over. Yeah.
Exactly. But we're not doing that.
Yeah.
Sticking to our source material today, we are going to ground this. This isn't magic, it's engineering.
It's engineering. That's the perfect way to frame it. And to really get it, you actually have to look back to, what, 1959?
Yeah, 1959, which sounds ancient.
In computer terms, that's basically the Stone Age. We were still using punch cards.
We were, but a computer scientist, Arthur Samuel, gave us this definition that just holds up perfectly. He said machine learning gives computers the ability to learn without being explicitly programmed.
And that word explicitly, that's the whole ballgame, isn't it?
It is.
Because normal coding is just a recipe. You know, if this, then that, you write all the rules. But here, we're flipping that. We give the machine the data, and it figures out the rules for itself.
Precisely. But here's where people get tripped up,
Mhm.
and the sources really hammer this home. People treat machine learning like it's this one single thing.
A monolith, like one AI brain you just plug in.
Exactly. But it's not. It's a toolbox. It's a whole collection of very different, very specific instruments.
You don't use a hammer to tighten a screw.
And you definitely don't use a giant neural network to predict a simple trend. You have to pick the right tool for the job.
So let's unpack this toolbox. The literature basically splits the whole thing into two massive categories to start. They call it the teacher approach and the discovery approach.
Or, as we call them, supervised learning and unsupervised learning.
Let's start with the teacher. Supervised learning. This feels pretty intuitive. You basically have the answer key, right?
You do. It's like teaching a kid with flashcards. You show them a picture of a cat, and you say the word cat. You show them a dog, you say dog.
You have the image and the label.
You have the label data. You are supervising the process. The machine's job is just to learn the mapping, so when it sees a new cat, it knows what to call it.
And then on the other side, you have unsupervised learning, the discovery mode.
Right. No answer key here. This is like dropping a kid in a library full of books in a language they don't speak and just saying, find the patterns.
That sounds almost impossible. How does it learn anything without being told what's right or wrong?
It's harder, but it's so powerful. You give the computer a massive pile of raw data, no labels, and you just ask it to find the structure that's already there.
So it's not looking for a cat because it doesn't know what that is.
No. It's just looking for things that are mathematically similar to each other. It finds clusters and groups and maybe some weird outliers all on its own.
I definitely want to get into those outliers later. But let's stick to the supervised side of the garage first. The source material calls the first one the hello world of machine learning.
Linear regression.
Yeah, this took me right back to high school algebra. Just drawing lines on a graph.
It should. It's one of the simplest and oldest tools. At its core, it's just about finding the best trend line to describe a set of data.
The source uses a financial example here, charting Bitcoin prices.
Right. So just picture a chart. The x-axis on the bottom is time. The axis on the side is the price.
Okay.
And you just plot a bunch of dots for the price on different days. You get a scatter plot.
So just dots all over the place.
Exactly. And linear regression is just the math of drawing the straightest possible line right through the middle of that mess of dots.
And the point is prediction. Once you have the line, you can look at a future date, go up to your line, and see what the price should be.
Spot on. The key takeaway here is that linear regression is for numbers, continuous variables, how much, how fast, how many.
But not every problem is how much. Sometimes it's a simple yes or no. And that's where the next tool comes in, with a kind of confusing name, logistic regression.
Yeah, the name is so misleading. It sounds like it should be the same thing, but it's not. It's a classification technique.
So it's making a choice.
A choice. Is this email spam or not? Is this tumor malignant or benign? A versus B. And a straight line just doesn't work for that.
Why not?
Because a straight line goes up forever. You could get an answer like, I'm 150% sure this is spam.
Which makes no sense.
It makes no sense. So instead of a straight line, logistic regression uses something called the sigmoid function.
Which is just an S-shaped curve, right?
So it's an S-curve, yeah. One that's squashed so that it's always between the numbers 0 and 1.
So it forces the answer to be a probability.
Exactly. No matter what data you feed it, the output is always a probability. If it spits out 0.9, it's 90% sure it's spam. It's the go-to for those kinds of decisions.
Okay, so we have lines for trends, S-curves for probabilities, but what happens when the data is messier? The source brings up support vector machines, or SVMs. This also seems to be about drawing lines between groups. Why do we need another tool for that?
Because logistic regression is, well, it's a bit sloppy.
Sloppy.
It's happy as long as the line it draws separates the two groups. It doesn't care if that line is just barely skimming the edge of the data. It's like a C-minus student.
I passed, didn't I?
Exactly. But an SVM is a perfectionist. It's obsessive. It doesn't just want a boundary. It looks for the widest highway it can possibly draw between the two groups.
With the widest margin.
It maximizes that margin, the empty space between the line and the closest data points on either side.
And those closest points, those are the support vectors.
That's where the name comes from. They literally support the boundary. And by forcing that margin to be so wide, the model becomes much more robust and less sensitive to outliers.
Now, there's a concept here that I found. I mean, it's just brilliant, the kernel trick. The source calls it a way to solve impossible geometry.
It is one of the coolest ideas in the field.
Mm.
So imagine you have a sheet of paper.
Okay.
You draw a cluster of red dots in the very center, like a bullseye.
Mm.
Then you draw a big ring of blue dots all around them.
Okay, picturing it. A red sentinel blue ring. There's
Okay.
there's no way I can draw. It's a single straight line to separate the red from the blue.
Impossible. Not in 2 dimensions, you'd have to draw a circle. But the kernel trick projects that data into 3D. So imagine lifting those red dots in the center up into the air so they're hovering over the paper.
So the red dots are floating and the blue dots are still on the desk.
Right. Now, can you slide a flat sheet of paper, a plane, between the floating red dots and the blue ones on the table?
Oh, yeah. Easily. I can slice right between them.
That's the trick. It maps complex data into a higher dimension where a simple line is possible, does the math, and then maps it back down. It lets a linear tool solve nonlinear problems.
That is incredibly clever. It feels like cheating, but with math.
It's just elegant engineering.
All right, let's switch gears to a tool that feels less like geometry and more like social dynamics. The source calls this one the new kid in school algorithm, K-nearest neighbors.
Or KNN. I love this one because it's so intuitive. It's what we call lazy learning.
Lazy. That doesn't sound like a good thing.
In this case, it is, sort of. It just means there's no real training phase. Most algorithms study the data and build a model before you ask them anything. KNN just memorizes the data and waits.
So it does nothing until you ask it a question. How does it decide anything?
Well, the analogy works perfectly. You walk into a new school cafeteria, you don't know anyone, you have no label, you sit down.
Okay, I'm sitting.
Now you look at the 5 people sitting closest to you, that's your K.
Yep.
K equals 5. If 3 of them are geeks and 2 of them are skaters,
Then the algorithm just assumes I must be a geek.
yep, it classifies you based on the majority vote of your nearest neighbors.
That seems almost too simple. Does that really work?
It works surprisingly well, especially for small data sets. But here's the catch. Because it's lazy, when you ask it a question, it has to do all the work right then and there.
It has to measure the distance from me to every single other person in the cafeteria.
Every single one. So if that cafeteria is actually a stadium with 50,000 people,
It would take forever.
it scales terribly. It's great for small stuff, but awful for massive data sets.
Let's move to something with a bit more transparency. We hear a lot about black boxes in AI, where we don't know why a decision was made, but the source calls decision trees a white box model.
Yes, and this is so important for fields where you need an audit trail, like banking or healthcare. A decision tree is basically just a flowchart.
The example in the source is a bank deciding on a loan.
Right. You start at the top, the root node, with a question. Is the credit score greater than 700?
Yes or no?
If yes, you go down the left branch. If no, you go right. Then you have the next question. Is income greater than 50,000?
And eventually you hit a leaf at the bottom that just says approve or reject.
Exactly. And the power here isn't just the decision, it's the explanation. If a customer asks why they were rejected, you can literally show them the tree. You can trace the path with your finger.
It's completely interpretable. But the source mentions a big risk here called overfitting.
There's always a trade-off. A single tree can end up memorizing the training data too well. It gets obsessed with the little quirks and noise in that specific data.
Like studying for a test by memorizing the sentences in the textbook instead of the actual concepts.
That's a perfect analogy. If the test questions are phrased a little differently, you're toast.
So how do you stop the tree from obsessing over those details?
You stop relying on just one tree. You plant a whole forest. a random forest.
Which is literally just a collection of many decision trees.
Hundreds of them, yeah.
Yeah.
And you train each one on a slightly different slice of the data. When it's time to make a decision, you let all the trees vote. It's the wisdom of the crowd.
So one tree might be wrong because it over-memorized, but the average of 500 trees is probably going to be right.
Precisely. It smooths out the errors and gives you much higher accuracy. But, and here's the trade-off.
You lose the interpretability.
You lose the white box.
Yeah.
It's impossible to explain a decision that was made by 500 different trees all voting together.
So we trade explainability for accuracy. That seems to be a recurring theme here.
It's the central tension of the entire field.
Before we leave the supervised world, there's one more tool mentioned that's famous for dealing with text. Näive Bayes.
Ah, yes. The original spam filter champion.
Why naive? Seems a little insulting to the algorithm.
It is a bit. It's called naive because it makes a big simplifying assumption that all the features, in this case, all the words in an email, are independent of each other.
Meaning it assumes that the word Viagra appearing has nothing to do with the word pharmacy appearing.
Right, which is obviously not true in the real world. Words are connected. But by making that naive assumption, the math becomes incredibly simple and fast.
And it still works.
It works remarkably well for things like text categorization. It just calculates the probability that an email is spam given the presence of certain words, and it's fast enough to do it for millions of emails.
All right, let's cross the aisle. We're leaving the land of answer keys and labels. We are now in unsupervised learning.
The land of discovery.
And the big tool here is clustering, specifically something called k-means.
This is all about finding structure you didn't even know existed. So imagine you're a giant retailer like an Amazon.
Yes.
You have millions of customer purchases, but you haven't actually categorized your shoppers.
I just have raw data, and I want to know who my customers actually are.
Exactly. You can't use supervised learning because you don't have the labels yet. You don't know who's a bargain hunter or a new parent.
So you just feed all that raw data into a k-means algorithm.
You do. And it looks at all the purchasing behaviors, and it naturally groups or clusters people together based on how mathematically similar they are.
So it might find a cluster of people who all buy diapers and beer on Friday nights.
Right. Or a group that only buys high-end electronics during flash sales. It doesn't label them. It just says, hey, these 5,000 people all act the same.
Yeah.
Then a human looks at the cluster and says, that's our new parent group.
This leads to what I think is one of the most critical applications in the source material, anomaly detection.
This is massive for security and fraud detection.
The source uses a really vivid example about a zoo.
Yes. So imagine a data set full of thousands of photos of tigers. If you show it a picture of a white tiger, the model sees that as a novelty.
It's rare, but it's still a tiger.
It still fits the general structure of the tiger cluster. But if you throw in a picture of a horse,
That's an anomaly. It's fundamentally different from everything else.
it stands out like a sore thumb. And this distinction is critical for catching what the source calls sleeper cells in fraud. This part kind of freaked me out.
It should. This is why supervised learning alone isn't enough. With a supervised model, you can only catch the types of fraud you've seen before, the ones you have labels for.
So if a criminal invents a totally new type of scam,
Your model is completely blind to it. But these sleeper cells are accounts that might look legitimate on the surface. They mimic normal users.
but maybe they were all created within milliseconds of each other, or they all log in from the same weird IP range, subtle connections.
They haven't done anything illegal yet, so a supervised model just sees them as normal.
But an unsupervised clustering algorithm looks at them and says, wait a minute. These 50 accounts are clustering together in a way that normal users just don't. It spots the structure of the attack before it even happens. It finds the horse in the tiger enclosure.
That is such a powerful difference. It's proactive instead of reactive.
Exactly.
Okay, we've arrived. The heavyweight champion, the tool that's in all the headlines, neural networks.
Couldn't leave this one out.
The inspiration here is the human brain, right?
Loosely, yes. You have nodes that act like neurons and connections between them that act like synapses. You have an input layer for the data, an output layer for the answer, and then these hidden layers in the middle.
And when we hear the term deep learning, that just means
It just means there are many hidden layers. A deep stack of them. The more layers, the more complex the patterns it can learn.
the source highlights a really important graph about performance here. Why is deep learning so dominant right now?
It all comes down to data volume. With traditional algorithms, like SVMs, their performance tends to plateau. You can feed them more data, but eventually They just stopped getting any smarter.
They hit a ceiling.
They hit a ceiling.
Oh.
But the graph shows that with a big neural network, as you feed it more and more data, its performance just keeps climbing. That's why it's powering things like self-driving cars. They need internet-scale data.
But we're back to that black box problem again, aren't we? Except on a much bigger scale.
A much bigger scale. If a neural network tells you a Kickstarter campaign is going to fail, it can't really tell you why. The decision is spread across millions of tiny calculations in those hidden layers. It's totally opaque.
Not like the decision tree where you can trace the logic.
Not at all. It's like mathematical intuition. It knows the answer, but it can't show its work.
So wrapping this all up, we've unpacked the toolbox. We have the hammer, the screwdriver, the power drill. How does anyone choose?
It just comes down to the problem. There's no single best algorithm. It's about your constraints.
Yeah.
If you need to explain a decision to a regulator, like why a loan was denied,
You have to use a decision tree. You need that white box.
you need to be able to point to the rule that was broken. But if you have millions of images and you just need to find all the cats,
You grab the neural network. Accuracy matters more than the explanation.
and if you're hunting for a new kind of cyber attack you've never even seen before,
You go unsupervised. You look for the anomalies and let the data speak for itself.
the real art of machine learning isn't just the coding. It's knowing which tool to pull out of the box. Understanding those trade-offs between accuracy, speed, and interpretability.
Before we wrap, I want to leave our listener with this one provocative thought from the source material. It brings this black box risk home.
The dilemma of trust.
Exactly. We're using these opaque algorithms for really critical things now. Hiring, criminal justice, medical diagnoses. We're handing over authority because, frankly, they're more accurate than we are.
They beat humans at the task.
But if we can't trace the decision path, if we don't know why the machine rejected a resume, it makes the whole system fragile. If it makes a mistake, we don't know how to fix it because we don't know what broke.
It's a huge trade-off between efficiency and control. We get better answers, but we understand the reasoning less and less.
So the next time an app predicts what you want to buy or a system flags your credit card, just take a second to wonder. Was that a tree you could read, a neighbor you sat next to, or was it a black box that made the call?
And if it gets it wrong, will anyone ever know why?
Thanks for diving in with us. We'll see you next time.